All right, I think we will start the event. If other people will join during my introduction, I think that's fine. So for everybody who's here, welcome. My name is Yuri Brakanov. I'm the president of the EAGE Local Chapter Netherlands, and tonight we are organizing an event together with DGB Earth Sciences. We have two amazing speakers lined up for you, Marieke van Hout de Groot and Paul de Groot. And well, I will give the floor to them in a little bit, but first I want to quickly go over some things specifically about the EAGE. I would like to give some announcements for upcoming events, and then we will go into the actual talk today. Before we start, I would like to give a shout out to Dong Chang and Florencia Balestrini, two members of the EAGE Local Chapter board, who have really done a lot to help organize today's event. So thank you, Dong and Florencia. All right. So first of all, we are a local chapter of the EAGE. What is the EAGE? It's a non-profit organization for geoscientists and engineers, and they organize many events throughout the world on these topics. The annual meeting next month will take place in Oslo, but there's also many other conferences and workshops that they organize. There's many benefits to being a member. You can see some of these on the screen here. If you're not a member yet, I would strongly recommend you become one. Because of all of the upsides that it has. And EAGE is often represented in the community by local chapters. For example, we are one for the Netherlands, but there's also chapters in London, Paris, Oslo, Aberdeen, and Germany, just to name a few. And these are the more senior chapters, but there's also chapters specifically aimed at students. Here in Delft, we have one for called the DOCS, the Delft Organization of Geophysics Students, but there's also one in Aachen, for example, and we also like to collaborate with those. So whether you are a professional member, a student member, there's usually a chapter located near you, and it's a great way to become involved with the community and stay afloat of the many events that are being organized every month. If you would like to join the community, either our chapter or any of the other chapters, here is some of the contact information. The only requirement is that you are a member of the EAGE. So again, I would give a strong recommendation of you becoming a EAGE member. Let's see. Our chapter, the Local Chapter Netherlands, is very easy to join. We have a LinkedIn where we post about our events. We also have a website and a newsletter. If you're interested in future events that we're organizing, you can send an email to eaglcnetherlands@gmail.com, and you will be added to the mailing list. And you will be kept afloat of any events that we are organizing in the near future. Speaking about upcoming events, I want to mention a few. First of all, it's the NL Energy Day 2024, which is taking place on the 17th of June. This is organized by PGK and the SPE Netherlands section, but we gave some support for organizing this event. It's about the way that we use energy in the Netherlands and well, what that energy demand is going to be in the future and how we societies can well, play a role in that. So if you're interested, I recommend you visit nlenergyday.org to see the program and find a link for registration. I mentioned the EAGE annual that's taking place in Oslo this year. We are going to be organizing a special event, a open panel where we discuss about all the benefits of being a local chapter, some of the challenges and some of the ideas that help foster these local chapters. And we do this together with the local chapter of Paris and of Oslo. So if you're going to the EAGE annual, I hope to see you there. It will be, like I said, an open event, and the title of the event will be Local Chapters Dialogue, Sharing Journeys and Best Practices. More information will be in the EAGE annual program. And speaking about conferences, another important one that's coming up is the GET, the Global Energy Transition Conference. It's going to be the 5th one, and this year it will be organized in the Netherlands. It will have 4 major themes: carbon capture and storage, geothermal energy, hydrogen energy storage, and offshore wind energy. I'm also pleased to tell you that we as a local chapter have been asked to organize a session during this event, which will most likely take place. We are currently getting together the speakers and organizing the actual program. So keep an eye out for that. We will inform you as soon as we have more news about that. Well, with all these announcements out of the way, I would like to go into the actual meat of tonight's agenda, which is the technical talk by DGB and by our speakers Marieke van Hout de Groot and Paul de Groot on the past, present, and future of AI in seismic studies. Their talk will last about 40 minutes, and after the talk, there will be an opportunity for questions and answers and to have a discussion. If you have a question, please use the question and answer tab in Teams. Type your question in there, and at the end of the event, we will unmute you so that you can ask your question to the speakers. During the event, we will keep the mics muted so that there will be no disturbance to the speakers as they are giving their talk. All right, so to introduce the speakers, well, our speakers are Marieke van Hout de Groot. She holds a M.Sc from the Behavioral Science faculty of the Technical University of Twente, where she had a focus on statistical research. And aside from studying at Twente, she also did several courses on geological interpretation of seismic data at the TU Delft, after which she started her career at the Geoscience Department of TNO as a junior communication specialist. She also was a member of the EAGE as a student affairs coordinator. More recently, in about 2012, she joined the DGB as a marketing employee, and she has in the meantime managed to work her way up to Executive Vice President of Asia Pacific region and Chief Marketing Officer. And she has a special interest in machine learning and geothermal energy. Our second speaker is Dr. Paul de Groot, who holds an M.Sc and PhD in geophysics from TU Delft. He has over 30 years of experience in advanced seismic interpretation and quantitative interpretation, sequence stratigraphy, and AI. He originally started his work in Shell, where he has worked over 10 years in various technical and management positions. And after that, worked 4 years as a senior research geophysicist for TNO before he co-founded DGB de Groot en Bril in 1995. He has authored a great deal of papers on geophysical topics. He has also co-authored a patent on seismic object detection, and he is a co-author of the book Soft Computing Techniques in the Oil Industry. So, as you can tell, these speakers are more than qualified to give us a very interesting talk tonight. So with that, I would like to hand the floor over to Marieke and Paul, and I wish you all a very well, interesting evening. So Marieke, Paul, if you could please, yes.
Jullie, thank you very much for the lovely introduction. I hope you can see my...
Yes, we can.
Sorry, yeah, I was clicking quickly towards the beginning of this presentation. So I will start things off by telling you a little bit about who we are as a company and our software OpendTect. And after that, Paul will delve into the fun part of this webinar. As you said, this entire presentation will take approximately 40 minutes, after which we will open the floor for questions. So who is DGB? DGB is a privately owned company founded in 1995. We are the company behind OpendTect, the world's only open source seismic interpretation platform. We are a company with an international footprint with offices in the Netherlands, the US, India, Malaysia, Vietnam, and we have agents around the world. I would like to start this presentation with telling you our origin story. In 1991, Paul was working for TNO, the Dutch research organization, where he was pursuing his PhD. His research focused on the use of neural networks and other soft computing techniques with applications in the oil industry. And in 1995, he founded his own company based on this research. In 1998, a terrible accident occurred in the North Sea involving Statoil, nowadays Equinor. During an oil operation, they hit a gas pocket, causing their entire drilling rig to collapse into the ocean. After this, an investigation was launched to figure out how this could have happened. And during the investigation, they discovered that they could find vertical noise trails in the seismic, which indicated gas leaks rising towards the surface. These noise trails, known by most of us as chimneys, were initially mapped by hand by stochastically. However, this was an extremely labor-intensive process, with interpreters taking up to 6 months to map just a very tiny section. So that's when stochastically contacted DGB to develop an AI solution. We created a supervised machine learning solution that trained an algorithm to distinguish chimneys in seismic data. And this innovation led to the creation of OpendTect, making us pioneers in this field. Since then, we have had time to continuously update our solutions. And with enhanced computing power, we now also offer deep learning solutions. So since the start in 1995, OpendTect has evolved into a comprehensive seismic interpretation system, offering advanced workflows for attribute analysis and data enhancement, quantitative interpretation, global interpretation, sequence stratigraphy, machine learning. And additionally, OpendTect also serves as a robust development platform, enabling plugin development in C++ and machine learning model development in Python. OpendTect operates on a freemium business model. The core software is free, allowing anyone to download and start using the software. So there are absolutely no strings attached. And all the essential tools that you expect to find in a seismic interpretation platform are readily available. This approach has helped us to build a very large user community. Now, in addition to the free platform, we also sell a commercial version called OpendTect Pro. This is built on top of the free version. And OpendTect Pro can be further enhanced by either renting or purchasing advanced plugins. And these plugins are developed by DGB or third-party vendors. We also invite companies to come and join our group and build their own plugins and sell them via us. We also invite universities to build free plugins, which are accessible to all our free users. So we make our money by selling and renting our commercial software and by performing geoscientific services and doing research and development work. The seismic interpretation software market is a multi-billion-dollar industry, and the number of seismic interpretation users is estimated around 100,000 worldwide. And this number is rapidly growing beyond the E&P industry, with users from the mining industry, the engineering industry, and the geothermal industry, all of which are now also focusing on machine learning. Now let's have a look at our users. Since we incorporated our open source model in 2003, our user base has pretty much exploded exponentially. We now have more than 50,000 unique downloads of OpendTect from more than 172 countries around the world. And thousands of these users are open source users, but we also have hundreds of commercial users, ranging from national oil companies and majors to R&D institutes to independent consultants. We are really dedicated to training the next generation of geoscientists. And to support this mission, we have provided over 4,000 academic licenses to more than 500 universities around the world. The graphic shows where the universities who are using our software are located. The licenses that we give out for academic use are exclusively for academic use and can only be requested by an accredited faculty member on signing our academic license agreement. Additionally, we offer special R&D deals for universities and research institutes that are receiving funding for their research projects. So for more information about this, you can send us an email either at academic.licenses@dgbs.com or you can visit our website at dgbs.com. So looking at our commercial users, you will see that almost all the major players in the E&P industry have licenses for our software. Throughout the years, we have won several awards in recognition of our pioneering work in AI. Some noteworthy ones are mentioned here, like the SAG Achievement Award in 2016 and the EAGE Louis Cagnard Award in 2018 for our best poster work, specifically on chimneys. And here's just a small sample of what our clients say about us, starting with the Chief General Manager of ONGC, the national oil company in India. He says that even having more than 35 years of experience in the field, he has never come across such innovation solutions as we offer. Leon Thompson, former SEG president, states that OpenTect provides state-of-the-art pattern recognition tools to complement your eyeball quantitatively. And Mike Klein says having OpenTect's attribute tools such as ridge enhancement can really make a difference when deciding where to drill. So this is just my small introduction, and now the fun part starts, where Paul will dive into AI. Paul, the floor is yours.
Thank you, Marieke. Let me share my screen. Can you see my screen, Marieke?
Yes, I can.
Good. Okay, this is where we were. I'll talk about past, present, and future of AI in the seismic business. And I'll start with a few definitions and sketch the history. And I'm doing that on the basis of this Gartner hype cycle. What you see in this graph is the expectation of a new technology versus time, and the time axis on the x-axis can be tens of years. It starts with an innovation trigger, and then people get excited and everybody jumps on it, and expectations increase with new innovations until at some point something happens or people get disillusioned by the technology not quite delivering what they expected, and then we dive into a trough of this disillusionment. Only the diehards stay on, and they continue to develop tools because every technology has at least some good things in them. And finally, this new technology is then accepted in the mainstream technology. What I would like to discuss here is where are we in this Gartner's hype cycle if we look at the AI business. But before doing that, I'll define a few things. And I'll start with artificial intelligence, which is the computer science that deals with trying to mimic human behavior in a computer. So not just intelligence, but evolution also, and social behavior. A subset of that is machine learning, where a model or machine learns from data and statistical techniques to improve a certain task that it is given. And this is without explicitly programming the machine. It's just based on the data. And deep learning, again, is a subset of machine learning, which has emerged a couple of years ago, where the models become larger and larger. Now we are having models with millions of parameters that can be tuned on a specific task, learning on vast amounts of data to do something. On the left, a small sketch of this subfield of machine learning, which is the main toolbox that we are using. And within machine learning, we recognize two main learning approaches. There is supervised learning and unsupervised learning. Supervised learning means that we need to provide the algorithm, the model, with examples. And this can lead to a classification of the data, but it can also lead to a quantification of the data. And then we talk about a regression problem. In contrast, unsupervised learning, we don't have any labels, no interpretation examples. We only have data, and we're trying to find structure within the data. that is basically a form of clustering or segmentation. Now, what is machine learning good for? It is good for finding complex relationships and structures in datasets from different sources with widely varying accuracies and scales. And that is exactly what we are dealing with in our EMP business and in earth sciences. We are trying to come up with a geological model that must be consistent with all the data that we have, ranging from satellite images hundreds of kilometers to seismic data kilometers to well logs to core measurements to descriptive observation at outcrops and even microscopic levels. And all that information must be integrated, combined, and leading to a consistent geologic model. We use it in earth sciences for seismic facies clustering, finding anomalies in the data, creating chimney cubes, which can be interpreted in terms of fluid migration paths, rock property prediction, inversion, and many other applications. A few more definitions. Neural networks themselves are connectionist models, and they consist of a large number of small processing elements which are connected through a weight to another processing element. Very often they are combined in layers, as we see in the sketch on the right of a small neural network. And these networks, they are inspired by the brain metaphor, which means that they are trying to mimic what is happening in the human brain. 10 years ago, when you talked about neural networks, you talked about a network which is depicted here, which is now called a fully connected multi-layer perceptron. It consists of 3 layers, an input layer, a hidden layer, and an output layer. It's trained on examples, and the actual nonlinear transformation takes place in the hidden layer, where we pass the information through some kind of sigmoidal shape function, often in order to create the nonlinear relationship output that we are seeking. This is nowadays called a shallow neural network to distinguish it from the very large networks that are being built and used today. And these consist of many of these layers, not just the multi-layer perceptron type of layer, but also other types of layers, and even millions of parameters that needs to be tuned in order to find the relationships that we're looking for. We're talking about convolutional neural networks and UNets, 2 types that I will explain in a bit more detail during this presentation. Looking back at the history, artificial intelligence really is starting with computer sciences, with Alan Turing, the man behind cracking the Enigma code in World War II. And his work already started in the 1930s, and the early work was really theoretical. The biological neuron was discovered, its mathematical analog, the perceptron was described. And in 1969, there was a paper that suddenly started a phase of disillusionment after Minsky and Paper wrote a paper that said that the neural networks of that time could not solve a very simple problem, the XOR problem. So then everything slowed down a little bit, but it became of renewed interest in 1985 after the discovery of the backpropagation, which allowed us to train these neural networks using gradient descent algorithms. This led to new neural networks, the multi-layer perceptron, the radial basis functions, Hopfield, Cohonen, UVQ, Boltzmann. And then this continued for some time, but also this slowed down, at least in the seismic industry, although the neural networks kept on being used. The real breakthrough in the next phase came with the start of the convolutional neural network, and thereafter the increase in compute power and the release of open source libraries such as TensorFlow, Keras, Scikit-learn, PyTorch, which really accelerated research in deep learning neural networks and enabled us to do things which were not thought possible just a few years ago. So if I sketch this in a Gartner Hype cycle, then we are now already in the third cycle, and we started more than 90 years ago. I think at the moment it's difficult to predict what is happening next, but I'm pretty sure that artificial intelligence, machine learning is here to stay. It's far beyond just a hype. You can't put it back in the box, even if you think this is a Pandora box that has been opened because of the fake news and all the things that can be done with machine learning models. I think we have to embrace it, we have to live with it, and we have to be wary of the things that can be wrong and also a bit scary, such as fake news and Big Brother watching you because it recognizes everything that you're doing. Last week, Marieke and I were in China, and our host at some point said, well, this is the safest part of Beijing because there are cameras everywhere. And he was very proud of it. And I think as a Westerner, we are very scared of that kind of situation. That's what artificial intelligence can do. So we have to be wary, but we also have to embrace it because it is here to stay. So let's look at where we are right now, and then I'll give you also examples of a number of neural networks models that we use basically every day nowadays. So most people think when they talk about machine learning that we are talking about neural networks only, but that is not the case. There's a whole family of algorithms that fall in the category of machine learning, and neural networks and deep learning algorithms are just one part of it. I've selected 2 shallow solutions and 2 deep that I will go into a little bit more in depth. That is k-means clustering, which in our implementation is an unsupervised vector quantizer. And then the multi-layer-perceptron, both are shallow solutions. And then I'll go to 2 deep solutions, convolutional neural networks and autoencoders, and then specifically the U-net. So unsupervised vector quantizers are very akin to k-means clustering. These models also need to be trained. They are trained on a subset of the data. And once they are trained, you have found the cluster centers. You then pass the information through the model, and the model outputs which is the winning cluster. That can be, in this case, a number from 1 to 3, because we are clustering this small network here in 3 clusters. And the second output that we write out is the match, which is a measure of confidence. How confident are we in this clustering result? And that's a measure from 0 to 1. 1 is spot on. It's the input falls exactly on the cluster center, and 0 means it's as far away in the space as we can be. Now, what are we using it for? Mainly for unsupervised waveform segmentations, and that is requiring a mapped horizon. And relative to this mapped horizon, you are extracting a time gate, that is a waveform, and each of these amplitudes is then fed into a neural network, and the user specifies in how many clusters do I need to cluster this information. So this was already developed in the 1990s. Actually, this was even developed before DGB started, because this came in out of my PhD work. Now, why is this interesting? Because what we can do very quickly is apply this on the mapped horizon and see how the patterns in the seismic change along this horizon. We select the time gate relative to the interval that we want to characterize. So typically, if we have mapped the top of a reservoir, we would apply a time gate just a little bit above the mapped event and more below it. We train the model, and we ask it to cluster it, as in this case, into 10 different clusters. The only thing that we know then is that we see colors on this mapped horizon which need to be interpreted by us. And these colors, they correspond to the waveform centers that we have clustered it into. So we know that the purple pattern corresponds to this high amplitude model. And that combination of the cluster center response and the shape of the patterns triggers our geologic brain to do interpretation in terms of seismic facies and other things. So this is based not just on amplitudes, it's based on the entire waveform, so on amplitude, frequency, and phase. We can do that, and we have been doing this on 2D horizons for a long time, but we can also do this in 3D. So we can map an entire 3D interval and do waveform segmentation. Typically, when we do it in 3D, we don't limit ourselves to 10 classes, 10 segments. No, we go to 40, 50 different segments, which we then can analyze in detail to see the response changing, especially if we would slice through the data along horizons. And that's what I'm going to do in the next slide. So here we have on the left relative acoustic impedance, and on the right we have the response from the 3D segmented result. And we can now see the channels and their different seismic facies in quite more detail. And we can start to see, if we go from slice to slice, how this channelized system has been evolving over geologic time. So this is at a deeper level, and we see quite a chaotic pattern of channels that are interlinking. And if we go a little bit up, then we see the blue channel is now ending up in two lobes, and we have a cutoff Oxbow Lake, and the green channel over here is more becoming wider. And in yellow we see levees, we see spills, we see overbank deposits. So it helps us to do geologic interpretation, but again, it's unsupervised. It means that at the moment the patterns and the colors need to be interpreted. It's just helping us to do this kind of interpretation. Now, the second shallow neural network is the famous Multi-Layer-Perceptron, and basically this network, in the picture over here, we have a three-dimensional problem. We have two inputs, and we're trying to predict what is happening on the vertical axis. And the objective now is to find the optimal surface through all our training points. And that surface doesn't have to be a flat plane. It can be just a curved plane. In this case, we have a network with just 3 nodes in the hidden layer. In this hidden layer, the sigmoidal shape transformation is taking place, and during training we are updating the weights which are attached to these connections in such a way that we are stretching and squeezing these planes such that if we add them all together, we are constructing the optimal plane for all the training points. Once that is done, we have a trained neural network and we can apply it, and then any combination of input x1 and x2 will produce an output of y, the predicted value. We can use this type of techniques for classification. For example, we developed this for the seismic Chimney Cube, as Marieke mentioned, but we can also use exactly the same technique for depicting salt, for seismic facies classification, for faults, for bright spots, turbidites, basically anything that you can see in the seismic data, you can pick it and train a neural network. But you can also use these type of shallow neural networks, these multi-layer perceptrons, for quantitative problems. So in this case, on the left, I'm showing an example where we predicted porosity from acoustic impedance, and we trained it on the available well data. So we created a training set to convert acoustic impedance into porosity, and we applied a trained network to predict porosity from an acoustic impedance inverted volume. And on the right, I'm cheating a little bit because I did not create this example with a multi-layer perceptron, but you can do it. In this case, we used a different algorithm, but the result is the same. We have a data set with input well logs, and we train it, in this case, to predict pore volume from 4 input logs. And we can use that to predict missing logs. And what we're seeing here is a blind test well, where we see on the right column the overlay of the actual pore volume log versus the predicted pore volume by this machine learning model. Now moving on to deep learning, and I'm starting with the convolutional neural network. And in this particular case, we distinguish two different workflows for seismic analysis: image to point and image to image. And image to point means I'm going to extract a piece of seismic that can be a 2D section or a 3D volume around a clicked position, with a labeled position where the interpreter has labeled, this is what I would like you to recognize. And in this case, we have picked green points here, which are a seismic chimney. And in blue, we have picked counter examples. This is normal seismic response. It has not been affected by fluids migrating through it. That is an interpretation. These interpretation points are used as labels to train my convolutional neural network. I could also train a multi-layer-perceptron on this. If I use a multi-layer-perceptron, I would extract attributes at all these positions and pass them through my MLP model to train the model. If I'm using a convolutional model, I'm taking the actual seismic data, either a 2D section or in this case, a small 3D cube. And then you train this convolutional model to convert the seismic image into, do I belong to the chimney class or to the non-chimney class? And this happens in a sequence of layers. And the first layer is the most important one, that is the convolutional layer, in which the image, the seismic section, is decomposed into a set of filters. And during the training, we're updating the weight coefficients of these filters to find these filters. And these filters take the same function as the attributes that we need to process, compute ourselves when we do an MLP type of prediction. In a convolutional neural network, it happens inside the model itself to extract these features in the form of filters. Now, such a image to point workflow has the advantage that the labels can be interpreted quite easily. I can pick examples, but I can also, if the object is large, I can use a spray to get all these points sprayed. Or I could even use a seismic tracker to get an initial set of points. And what you see here in the small inset is the result of a seismic facies tracker that we have used to create labels. So this seismic facies tracker, it's called Taalweg tracker, is starting from a certain position, and then from the shape that it produces, we can do an interpretation. Like in this case, I can clearly see that this particular shape in blue is following a channel. So this would be a label for me to classify all these points as seismic channels with a blue, or sorry, with a positive amplitude, whereas the channel below in yellow would be the classification results of a channel with negative amplitudes. And so we can create different types of seismic facies. It is interpreted by the user, but these points can then be used as labels for a convolutional neural network to recognize or to classify the data, in this particular case, into 8 different seismic facies classes. And what we see here with the slider is sliding through this seismic facies cube at 2 different levels. So we have flattened this cube using our horizon cube technology, where we can map automatically hundreds of horizons, and each of these horizons can then be flattened so that we follow the same geologic timeline. And what we see in these different geologic timelines is how the system has evolved in terms of deposition seismic facies over geologic time. Now that was image to point, and the main problem with image to point is that it is fast in training. Oh, sorry, it is fast. Yeah, it's fast in training, and it's also easy to interpret, but it is very slow in the application phase, especially if I use 3D inputs. It can take many days to process an entire volume. So that is not really what we want in an operational environment. So we prefer to do something fast, and then image-to-image workflows are much better. But the problem with image-to-image workflows is that the labeling is much more difficult. So what is an image-to-image workflow? That means that we are putting something into the size, into the model, and we also get something out, which is the transformed output. The transformed output can be in the form of a classified result, like a fault cube. It can also be in the form of a quantitative regression output, such as a seismic inverted volume. Now let me try to explain how this works. So the type of neural network that most people at the moment are using is called a UNet, and that is falling under the category of an autoencoder. It consists of an encoding part, which is the left side of the U, and then a decoder part, which is the right side. In the left, we go in the first layers through a convolutional layer where we extract the features. Then we reduce the dependency on the exact positions of certain features by blurring the image a little bit, and we change the size. We go deeper, pass it through the bottleneck, and then we upscale it again in the decoder part. There are a couple of weights attached across so that we don't lose any information. And in the final part, we do a transformation just as in the multi-layer-perceptron with sigmoidal shape functions. So what can these type of neural networks do? They can transform a block of seismic data into a block of the same size with something completely different. They can learn to transform this from seismic into fault likelihood, or from seismic into impedance, or from seismic into whatever. Again, you need to have the inputs to train this. It can be 2D and it can be 3D and it can even be 1D input and output, but always the size of input and output is the same. An example, this is a 2D unit which was trained to recognize salt, and the interpretation was done on just one line, which is the line that you see. So we've mapped the outline of the salt. We transformed the seismic into a mask that is a section with zeros and one where it is salt, 0 where it is not salt. And then we trained the unit, which had a dimension of 128 by 128 samples, to recognize where is it salt and where is it normal seismic. The trained model was then applied to the entire volume, and it gives us the 3D output of the salt dome. We can use these 3D units also to convert 2D seismic into pseudo 3D. So the model then learns to interpolate this type of seismic. And in our model, OpendTect machine learning, our solution, we can do workflows for just working with wells, just with seismic, or the combination of seismic and wells. But we also have a library of pre-trained models, and this is where we see a lot of the future, because these models have been trained on a certain problem and they can be reapplied to an unseen data set and give you a result directly, for instance, to produce faults or to interpolate data or to do something else. And I'll show you a number of examples of pre-trained models. On the left, we have a UNet. All these models are UNets. A model that has learned to recognize faults from synthetic examples. So we have a simulated data set that has been offered to the model, and the model then learned this is seismic and the output is fault likelihood. And we apply this model to this seismic and we get fault likelihood as an output. Now this is after thinning algorithm. So it's really a one sample slice output, but you can see that it did a pretty good job in recognizing the faults. The slider that we see going from left to right is the application of a trained model which has learned how to interpolate seismic traces. It's also a 3D unit, and we've trained it on a dataset in Delft onshore, and we apply it to the F3 dataset offshore. So what we did here is we blanked artificially 33% of the traces, and then we filled it in with the machine learning model. And as you can see, you hardly can see any difference. So this model is really a fantastic interpolator. Now, this is my favorite. This is a model called EAGE, and the data that you're looking at is legacy data that we have retrieved from NLOC. It is near where I live. It's over the city of Almelo. And as you can see, the data is really, really noisy and bad. The EAGE model that I'm going to apply is cleaning up the data. It does a number of post-processing steps. It has learned to clean it up, increase the coherency of the data, remove noise, and make it better interpretable. Now, you can see this I could not interpret, but this I can interpret. And the nice thing about the application of these 3D units is that it is extremely fast. This took just a few minutes on my laptop. Another example which I find quite striking, also this is from NLOC. It is a model that removes migration smiles. And anyone who has seen seismic data recognizes these type of crisscross events. These are migration smiles. And this model has learned to remove these or reduce these. So let's first look at the circle under 1. This is after D-smile, this is before. And you can see how fantastically this has been cleaned up. Now let's look at 2, which is the actual target zone in this case. And also here we're doing a very good job. Makes it much easier to interpret. But now let's look at the middle in 3, where we have salt floaters. And also these have been tackled because they have the same dip as the migration smiles. So this is just to show you that you have to be careful with applying these models. They're very fast to apply. It's very easy to just test it. Does it help me or not? But you have to be careful because it can also tackle primaries, as in this case. The next model, also one of my favorites, it is removing multiples, horizontal multiples. And the alternative here is either I apply this model and 5 minutes later I can continue with my work, or I have to go back to reprocessing, spend $500,000, wait half a year and get the same result. So that's why we see huge potential for these type of models. And we think that acceleration of our work by operational geoscientists will be happening if we have more of these models that can be applied very easily and very quickly. And our software system, OpendTect machine learning, is built in such a way that experimental geoscientists can build these models using the tools that we have, either with the wells only or with the combinations of wells and seismics, or just on seismic. Once they have a model that is worth sharing, they can share it, and then operational geoscientists can reapply this, and that will decrease time, effort, and costs. So that is where we are right now. Let's have a quick look into the future. And I already mentioned the pre-trained models. I think there's huge potential for more models on the well side, on the seismic interpretation side, on processing, and also even on engineering side. We just have a small library at the moment, and we think this library will grow as the system matures and more people are doing research and willing to share these models with their peers. Secondly, I think that at the moment the workflows are still quite unwieldy, that you need to be an expert to understand and to do it. And in the future, I see potential, and we are actually going to develop this ourselves, interactive workflows. So the idea is that if you're applying one of these pre-trained models to your seismic, you will get the prediction of the fault likelihood, or you could have the prediction of a particular horizon that you're trying to map. But let's focus first on faults. So you get this image, which is the prediction of this is how good the model at the moment is. And then you can update your model by interpreting yourself on that data set. So you're interpreting sticks, and these interpretations will then immediately be used to create new examples to train your model further. That kind of training is not updating the entire model, it's updating only the last part of the model, and it's called transfer training. That's very fast. And it means that your model will be tuned to this specific data set. And as you are interpreting, the model is reapplied to your data, so you see immediately if it is helping you and how good the model is. Once you've done a couple of inlines and cross lines and you think, okay, it's satisfying, it does what I would interpret myself, then you apply the model to the entire data set and you have your fault likelihood result. And the same thing you could do with horizons. So you would have different models for picking different horizons. At least that is what I envision. Now, what is then the next step? The next step is like a ChatGPT for seismic. And this is what is called foundation models. And foundation model is not trained on labeled data. That's the nice thing about it, but it is trained on huge amounts of data. And the form of training is called self-supervised training, which basically is a form of unsupervised learning, in which the model learns to recognize certain features from the data itself. For example, if you're training on speech data, then you could leave out a word in the sentence and you'd ask the model to predict the word that you have left out. You can do a similar thing with images. You can just blank parts of the data and the model should learn to fill in these blanked parts. You have to do this on millions of examples, preferably from all over the world, to cover the entire range of seismic characteristics that are possible. And once you have trained such a foundation model, it has captured all the features of seismic data. And this model can then be tuned to solve different problems by training it on a very small subset of labeled data. And that is basically similar as what I've just shown there with the interactive workflow. You would train it on a few fault sticks that you have interpreted. And I predict that the interactive fault and horizon workflows will be more accurate when you start from a foundation model than you use one of the models that have been dedicated and trained to do just this one task. So the future is for foundation models, in my opinion. Now, my last slide, do we have to be afraid that we are going to be replaced by machine models? And that is an easy no. I'm definitely sure that is not the case. In my opinion, machine learning models only recognize patterns in the data, and they're really good at this. But just tracking horizons and faults is really not the essence of what we're doing. It's just a first step into the interpretation. The ultimate goal that we try to achieve is to transform all the measurements into a consistent geologic model. And that must be consistent with not just the seismic data, but all the observations, all the knowledge, everything that we know should be integrated. And I don't see machine learning models even coming close to doing that. Not now, not in the near future, and maybe not ever. What I do believe is that we, as human interpreters, must acquire new skills to use this technology effectively. I do believe that machine learning can be very beneficial. It can increase our efficiency, enable us to extract more information from the data. But you also have to have a proper understanding of the technology, because there's a real danger of producing rubbish in, rubbish out. And therefore, I think the more we know about how this works, the better it is to actually use it. And that's my last slide. So thank you very much. We're open for questions.
All right, Paul, Marieke, thank you very, very much for your talk. I really enjoyed it. To the people in attendance, please write your questions in the chat. And indeed, I already see the first one from Elham. I will unmute you so that you can ask the question yourself. Give me a second to find you. There you go. Go ahead. You can unmute yourself and ask the question.
Hi, good evening. Thank you so much for your nice presentation. I have one question about the, do you have also some project for using machine learning for digitizing the vintage images? For example, we have a lot of open source vintage image of the old seismic profiles that they are in the JPEG format or PDF format, and they are super old and they are in black and white version, but using them for interpretation in the software such as OpendTect or Petrel or other software has a lot of difficulty because of the low resolution and low quality of this image file. Do we have also this opportunity for using this method for digitizing this profile or not?
I like the idea. I think it's possible, but I've not heard anyone trying it or doing it. But I'm pretty sure that it's possible.
I use MATLAB code for doing this one, but unfortunately, MATLAB codes are super complicated, and the result is not really good. They are not really good result. Sorry. Also, I have another question. How much this model are accurate? How much they can have an error for using this machine learning for interpretation of the seismic profile, as you already told?
Yeah, also that is a good question as well. You have to work in a different mode than when you're using conventional statistical methods. So in statistical methods, you always have the same answer because you're just applying some kind of formula, and it gives you, based on the assumptions and the equations, a certain response. And a lot of people think that that's great because then they always get the same answer. What you do with machine learning, each time you train a model, you get a slightly different answer. So you have to look at the output a little bit differently, and you have to build in sufficient number of validation tests to ensure that what you are doing is correct. But in the end, if you do that, then most often your end result will be more accurate than what you can achieve with conventional statistical methods. And that is because in most of the conventional things, like for instance, if you do linear regression, you are assuming that your problem is linear, whereas in neural networks, it can be highly non-linear. It will just find the optimal solution for you. And that will give a more accurate result. But if you're not knowing what you're doing and you're not building in the validation tests, then yeah, maybe you get an answer, but the answer could be completely wrong. So you have to be very careful in evaluating how you're doing it, what you're doing it, and ensuring that you have validated it properly. So
yeah, the human
applying it to blind
components.
tests, yeah, but also applying it to blind test data where you can calibrate your result. These type of things are extremely important.
And the human components plays a major part in how reliable your test results are. As Paul said, if you put rubbish in, you will get rubbish out as well. So that's something to be aware of. And having blind tests really, really helps to make sure that you have a good model in place.
Thank you so much.
So Yuri, you are muted.
My apologies. Thank you. We also have a question from Steve. So Steve, I will unmute you. And you can ask the question that you just wrote in the chat.
Okay, am I live?
You are.
Hey,
Thank you
Steve.
for joining us, Steve. It's
Hi,
good to
Paul.
hear
Hi,
you.
Marieke. How are y'all?
Yeah, fine,
Steve is
thank
an
you.
old friend,
Nice to
so
hear
I
you.
apologize.
Yeah,
Lovely presentation as usual,
thank you.
and always a brilliant approach. I see a lot of potential for the technologies that have been developed here for more of a multi-physics kind of use, where we start merging the data we get and that we're interpreting in slightly different ways from gravity, magnetics, electrical, and putting that all together. And also for what I see as a evolving state of monitoring and evaluation of actual man-made structures in civil engineering. Because we have the sensor capability now to build all these data sets. I see people that are working on this looking for actually models, data sets, which will be of value to them. And it seems like that also represents kind of an avenue or a venue where we can really use this technology in kind of ground changing ways. Are y'all working with any civil engineering or construction companies? Have you thought about this particular
It's so
part
funny
of
you
our
should mention
technology?
that. We literally just won a pilot last week with high size, and we expect to do many more. And we're actually discussing with a mining company, a huge mining company whom I will not yet name, if we can do a pilot study. So yeah, this is definitely something we're really interested and excited about, and we think this has huge potential for the future.
Excellent, excellent. Okay, well, I figured as much, but I'm glad to hear that confirmed.
Thanks, Steve.
Thank you.
Thank you.
All right. I don't know if there's any other questions from the audience. Oh, I see Boris wants to ask a question. So Boris, you should have a mic now.
Hi, yes, do you hear me?
We do. Hi, Boris.
Yes, hi. I'm Boris Boulanger. I'm a geophysicist at TNO in Utrecht. And basically, I have a question about the fine-tuning that Paul discussed. I was wondering, what is your vision of the role of synthetic data in fine-tuning? Well, first in training, in doing the pre-training of models, and in the fine-tuning process. So what is the role of synthetic data in your workflows?
That's a good question.
Yeah. Me? You?
Paul, go. I think you will talk about
Yeah.
syntrock, and you're better in that than I am. So please go ahead.
Indeed. Yeah, we do have a forward simulating package called syntrock, and we published a paper on how we use syntrock in combination with machine learning to find a relationship between the seismic response and the underlying model properties. We use it mainly for reservoir characterization, and I think that's where syntrock, at least that approach, is very appropriate. Also for fault modeling, these fault models that we have several fault models that have been trained on simulated data, and they're performing quite well. Some of them start with simulated data and have then been tuned to real data. That's even better.
Yeah.
Yeah, I definitely see there is a role for simulated data, especially in the domain where you have so many parameters and knowledge that you can create good simulated data, but it's difficult to do it otherwise. It's more difficult on the larger scale. So I don't see that much potential for creating realistic simulated examples at the macro scale. So geological objects that can be seen on the seismic, that's way too complex.
Mm-hmm.
And that it's better to use deterministic methods.
Okay. Yeah, thanks. Yeah, and again, thanks for the very good presentation.
Thank you very much. Are you using our software, by the way?
Not yet, but I have some. We do have some intention to use it also for development of some machine learning applications. So maybe we get in touch in the future. Yeah.
Yeah, actually, TNO has our software, and we've been talking to Stefan Carpentier a lot. So if you want to start, I'm sure he will be able to help as well.
We are looking at it together. So.
Oh, perfect.
Yeah.
Good.
Thanks.
All right. I see that Bin Q has a question. So I hope I pronounced that name correct. So Bin, go ahead.
Yeah, that's correct. Thank you. Thank you, Paul. Thank you, Marieke. So, my name is Bin Q from the Petrol Explorer in Canada. So, I have one question about the potential of applying the physics-informed neural network on our seismic data, and see have you applied anything that technique on your software, and you see any improvement in terms of the accuracy of the prediction or classification? Yeah. Okay.
So first of all, hi. It's nice to hear you again, Bin. But I didn't quite catch the question. You're asking about a foundation model, or?
No, so because you're talking about the neural network, right? I see here we have quite advanced one is a physics-informed neural network. You heard about that? That one, no. Like we apply the physics law into the activate function.
Okay.
Yep. And then that one will have to increase the accuracy of the label and the prediction. Yep.
Yeah, I don't know this specific model, but I do believe in hybrid solutions. So the more physics we can put in into the model, the better it is. I'm convinced of that.
Okay. Yeah.
All right. I believe
so.
Steve,
That's it. Yeah. Thank you.
Oh, thank you for your question, Bin. I believe Steve had a question, and I believe let's make that the last question of the night.
Okay. I was just thinking in terms of the question that the gentleman asked about the simulated data, and I was often wondering if we couldn't create a better, or shall we say, a more robust fault imaged model from tank data, and then use that as your training, as your simulated data, if you will, to help drive some fault interpretations in similar environments. I mean, a lot of this comes back from the days when I remember it was actually tank data and some other work that allowed us to recognize that large growth faults were tending to soul out at 15 to 17,000 feet due to pressure, which was not something that we really understood prior to that. And that kind of data would seem very valuable from a tank model to be able to somehow project into our real data. Is that something anybody's tried?
No, but I think what you're saying, and I have not tried this or realized this, but there are these packages which can reconstruct data, and there's one which just works with images, and then you interpret your faults, and then it reconstructs the data back in time, so it stretches and squeezes and everything.
Spastic.
Yeah, and I can imagine that if you use snapshots of these as input and then try to go back, that could be very interesting as a learning example on how faults should be interpreted and whether it's realistic or not, because there's a lot of geology and physics behind these models, these solutions. It's not just drawing something. It's really, if you do it wrong, you will see it because your interpretation is wrong. And a lot of these examples exist, but have not been used. But I think they could be used for training models and go the other way. So yeah, there's a lot of things that are possible, but have not been tried, or yeah, or we are too afraid to do the work, because a lot of the work is really about doing it and preparing the data and harmonizing it and what have you.
The grunt work.
The groundwork, yeah.
Yeah.
Thank you so much.
Thanks, Steve. Pleasure to have you with us tonight.
Yes, indeed. Well, I think that is an excellent way to cap it off for now. So thank you all for the members in our audience for participating. Paul, Marieke, thank you so much for hosting this event with us and giving the talk. I enjoyed it a lot myself, and I hope to well see you again in the future. So
Thank you for organizing.
Yeah,
Thank you.
well, no problem. So once again, thanks for the EAGE Local Chapter board members who helped organize this event, Dong and Florencia. Thanks again to DGB for all their work on this event, and we hope to see you in the next one. And I wish you all a wonderful evening.
Thanks.
Thank you, Yuri, and
Good
thanks
night.
everybody. Good night.
Good night.